Shall I start?
Yeah, you can.
Yeah. Hello, everyone. Thank you for joining me today. Thank you, Kishale, for inviting me. I am Lokesh, a PhD student at IIT Bombay. I work with Professors Sunita, Sarawagi, and Abir. My research primarily revolves around causal inference, and today I'm excited to delve into the topic of treatment effect estimation, particularly focusing on treatments taking continuous values. This work got recently accepted at AAAI. Without further delay, let's get into the details of the paper. So firstly, what is treatment effect estimation? It is one of the pivotal challenges in causal inference, and it has impact in fields like medicine, economics, and social sciences. Treatment effect estimation is all about estimating the causal inference of treatment on an outcome. Let us consider an example. Imagine we are tasked with finding the most effective treatment for a certain kidney disease. We have two options, as we see in the slides, a red pill and a blue pill. The goal is to find which of these two pills is most effective in curing the kidney disease. As machine learning people, we'll hope to tackle this question using our secret sauce, that is data, right? So let's assume somebody went into the field and collected data about, let's say, 700 patients. And these patients are affected with kidney disease. One thing that is relieving to see here is we see that there is no imbalance in treatment assignment. That is, among the 700 patients, we see that roughly equal subjects. The we see that the patients are distributed evenly across the two treatments. So we can hope that we will be able to answer this question just using this data. Right now, let us look at the results of this study. We see that treatment B has 83% success rate as opposed to treatment A that just has 70% success rate. Now, from this experiment, can we conclude that treatment B is better? Well, somebody may intuitively think yes, treatment B is better, but let me convince you otherwise. The answer to this question lies in inspecting the data at a finer granularity, right? So we often have what are called as confounders in our data sets. For example, in this experiment, a confounder happened to be size of the kidney stone. It so happened that treatment A received challenging patients with larger stones as opposed to treatment B, which mostly received easy patients, right? So in general, confounders are variables that affect the treatment assignment and also influence the outcome. For example, if you have a larger stone, it's kind of likely that you may not be cured of the disease given either treatment, right? So these confounders screw up the treatment effect estimates if they are not accounted for properly. So for all matrix fans out there, the problem that we want to address is, do you want to suggest blue pill or the red pill to an arbitrary patient? We'll dive into how we can make this decision in a principled manner now. So the main hurdle in resolving the dilemma from a training data set is presence of what is called as selection bias. In causal inference context, we often refer to the training data set as observational data set. For example, in the experiment, we had data of 700 patients, right? So that data, we call it as observational data. We say that selection bias exists when the treatment assignment to patients happens in a biased manner. For example, we see in our context that easy patients with smaller kidney stones were treated with red pill, whereas challenging patients were treated with the blue pill. Such selection bias is often unavoidable in real life, right? So basically, the punchline is that real life observational datasets are going to be injected with selection bias, and we as researchers must provide in principle algorithms that reflect correct treatment effect estimates. The variables such as size of the stone in this experiment are referred to as confounders in the observational data. The key aspect to solve many causal inference problems, not just treatment effect estimation, is to come up with what is called as a causal graph, right? Simply put, a causal graph is nothing but a directed graphical model. If you're not familiar with graphical models, think of it as a graph that contains nodes representing variables or attributes that are relevant to a problem, right? But we say it is a causal graph when the arrows have richer semantics. In particular, we want the arrows in this graph to reflect causation. For example, in this graph, we see that there is an arrow going from t to y. This means that changes in variable t will affect what will affect the values that y can take. But if you change y, that will not have an impact in t, right? So we say the causation flows from t to y. Now, in this graph, let us shift our focus to this variable x. In our experiment, x is the size of the kidney stone. And this is one interesting part about x. We see that changes in x in this graph is affecting both t and y, right? This is the precise definition of a confounder. Confounders are those variables that influence the values t and y. Both t and y can take in the observational data set, right? And this kind of variables screw up. This kind of variables, in general, screw up the treatment effect estimates, and we need to account for them in a principled manner. Now, formally, this is a problem statement. Our objective is to estimate the variation in outcome that results from administering different treatments to patients. However, we have one challenge, that is, for every individual, you only have supervision for one of the two possible outcomes. But our goal is to model the y star that represents the difference in the outcomes, right? So the inherent challenge, or this is called as fundamental problem in causal inference. The challenge is that you don't have supervision for the target variable that you are chasing, right? Now, before getting into our setting, right, let's discuss one idealized scenario that is called as randomized control trial, right? In an RCT, selection bias does not come into play. So in RCT, what happens is the treatment assignment to patients is done randomly. So you flip a coin, and depending on the outcome of the flip, you assign treatments to patients. In this type of scenario, confounders do not exist, and estimation of treatment effects can happen simply by taking expectations from your observational data set, right? Particularly, if you have collected observational data following arbitrary treatment assignment, you can estimate the effect by just computing these two expectations, right? So you collect the patients that were assigned the blue pill, average their outcome. You collect the patients that were assigned the red pill, average the outcome. You take the difference that will give you effect.
Lokesh, your screen, your PPT you can't see. Can you share it again? Anybody can see it, or I'm the only one who can't?
Lokesh, your screen got unshared for some reason.
Sure. Let me share it again. Is it visible now?
Yeah, now.
Yeah.
Now.
So, yeah. So we were discussing about how to estimate effects in a randomized control trial. So as I told, in RCT, the assignment of treatments to patients happen arbitrarily, and under such a purely random assignment of treatments, there are no confounders, right? Basically, you assign blue pill and red pill arbitrarily to patients, and if your observational data is collected following an RCT, you can estimate the effect by just averaging the outcomes conditioned on the observed treatments, right? However, if confounding does exist, these expectations will give you misleading insights. As we saw earlier, if I roll back to the previous slide, right? we saw that here treatment B has 83% efficacy as opposed to treatment A, but then you could not conclude based on the simple expectations because the observational data here did not admit random assignments. Now, I would like to introduce you a closely related concept, that is estimating conditional average treatment effect. What we saw earlier was average treatment effect, but here you want to estimate effects conditioned on certain covariates, right? So we want to estimate effects conditioned on this variable x here. And then, for example, you may be after a query where you want to find effects for patient that are aged between, let's say, 40 and 50. Now, when you're presented with an individual that falls in this age group, you want to recommend the best treatment to him, right? Now, we are interested, in particular, we are interested in understanding the effect of treatment given a particular patient characteristic X. Now, to estimate this conditional average treatment effect, it turns out that we need two properties to be followed by the observational dataset. First assumption is overlap, and second assumption is conditional ignorability. The first assumption states that the likelihood of observing any treatment for a given patient should be non-zero, right? Conditioned on any patient characteristic, you need non-zero samples to be observed in the observational dataset. The second assumption, that is conditional ignorability, it is a bit more complex. We'll understand it with an example in the next slide. Yes. Now, let us understand what it means to achieve conditional exchangeability. And we'll assume in this slide that age is a confounder, right? So here in this diagram, I have shown a particular subset of the observational dataset consisting of just the elderly individuals, right? Now, among this, for example, here I have 12 elderly people, and it so happened in the observational dataset, 6 people were assigned the red pill, and remaining 6 people were assigned the blue pill. Conditional exchangeability means that within this subset, if we were to swap the treatments, then the expected outcome should remain unchanged, right? It turns out that under this assumption and the overlap assumption that we saw in the previous slide, conditional average treatment effect is estimable from the observational dataset. So our problem is to estimate treatment effects for continuous treatments, right? So the one twist in the problem now is that our treatment variable t can take continuous values, and this setting adds a layer of complexity to an already intricate problem that we saw in the previous slides. And this requires us to propose novel estimation strategies. We'll see how to estimate causal effects for continuous treatments now. So regardless of if you're dealing with continuous or discrete treatments, a general approach to tackle treatment effect estimation is this, right? The first step is to fit a model that estimates the outcome for a specific treatment T assigned to an individual X, right? So this step involves training machine learning models using the observations in the observational dataset, right? Once you have fit this model, you will estimate the treatment effect by using the fitted model twice in 2 separate instances, right? Once you will probe the model for T, and then you will estimate the outcome under T prime. You will compare the predicted outcomes under the 2 treatments, and that basically forms your effect, right? So for a X, we are estimating the difference in outcome as you change the treatment from T to T prime. This effect is estimated by this difference quantity, right? And remember that F is a model that you fit on the observational data that was given to you. So in our problem, the architecture that we used is VCNet, and VCNet is one of the state-of-the-art models that is proposed in literature. This model comprises two modules. The first one is a representation network that embeds a covariates X into an embedding space Z. Then we have the outcome network eta. So eta, when it is given with the embedding Z and a treatment T, it predicts the outcome Y corresponding to it. Now, it is interesting to see, how VCNet processes the treatment and uses it to learn the eta model. I'll not get into the details, but I would encourage you to check out the details in the paper. So,
Hey,
yeah.
Sorry, actually, I have a doubt.
Yes.
So in the previous slide, can you?
Yes.
Yeah. So when you're learning this f theta, so how do you make sure that the f that we have learned is actually what we wanted to learn? Like, how do we validate the efficacy of this f function?
So we are given with this data, right? So for
Right.
every X, you have Y under one of the treatments.
Mhm.
So you will fit the function F only on the observed Y's. You will not fit the Y on F on Y star.
Okay. Y star is basically a difference between the treated and the control,
Exactly. Yes.
right? And we are fitting
Right,
it on the Y.
Y's, yes. Y under one of the treatments. And your question is right. For example, in this scenario, where you will have outcomes corresponding to the red pill for EC patients that have smaller stones, right?
Right.
So the function F will have a good accuracy on red pill when the patient is kind of having EC case. The accuracy of red pill will suffer if it is presented with a challenging patient. That is the problem with this problem statement.
I get that. But since we have learned this F, and then I think we are trying to see the counterfactual of each of the samples that we have in the data set.
Yes.
Now, whatever it has predicted, that it says that okay, if you give a treatment A versus B, this is the delta that you will see in the effect.
Exactly. Yes.
How do we make sure that this delta is accurate?
We cannot make sure because in practice you cannot you don't have supervision for delta.
Okay, so there's no theory on this.
For example, in this setting, you cannot give both red pill and a blue pill to the same patient.
Yeah.
The theory. Yeah. A theory is at least for this problem, if it so happens that X is the only variable that confounds T and Y. If this assumption holds true, then we can derive in principle answers to this problem. But even this assumption is not testable in causal settings.
Right.
You may always have a hidden variable that still affects both T and Y, and we don't know. What is that hidden variable.
Okay. Got it.
Yeah. So people not blindly, people I think make this assumption, conditional ignorability. So this assumption should come from domain experts. If this assumption is satisfied, then we can talk about accuracy of delta.
Sure, got it.
Yeah. Any other question?
But then again, if we know that all these assumptions are holding, there's some domain expert that has told us that all the confounders are there.
Yes.
We have incorporated that data in that information in the data in the model. Then also, can we comment on the accuracy of the K that we are getting from the model?
So if conditional exchangeability holds, then I can take the difference in the average Y corresponding to these 12 patients.
Okay, and that reported number is assumed
valid.
To be true. Okay.
Yes, that is true. Okay. Because when I swap the patients, right, expectations should match.
Right.
Yeah. And if the expectations match, then I can simply take the difference.
Okay, got it. Got it.
Yeah.
I have a small question.
Yes.
Hello. Yeah. So
Yeah.
what if we do multiple RCTs? Because we won't be able to do this conditional verify this conditional exchangeability, right? Because we
So
won't be able to
if
give
you do
tuples.
RCT, then you don't need any of these assumptions. If you do RCT, you
Okay.
can
Yeah, multiple
compute the
RCTs.
delta. No, one RCT will be sufficient.
Mhm.
So under RCT,
Yeah,
just
but then in
yeah. So if
yeah, but
let's say
then
you computed
in
this,
Mhm.
yeah, please go ahead. Yeah.
Yeah. So then in RCT, then these underlying latent variables wouldn't be taken into consideration, like the case of heart, kidney stones, and those kind of things. But if you do multiple RCTs, then in one case, say group A might get hard cases and there can be a chance that in another case, group B might get hard cases, and it would all cancel out, right? So that is what I was thinking.
Yes. So if you do RCT, you are assigning the treatment based on the toss of a coin, as we saw in this slide.
Yes,
Yeah.
yes.
So the observational data, you had a bias in terms of assigning red and blue pill, right?
Mhm.
Whereas with the RCT, the treatment assignment is happening by flip of a coin.
Yeah.
So then
So
under RCT, the variable X will be null set. There are no confounders because there are no variables that affect both treatment assignment and Y.
I see. I see. But then, I mean, we can take some feedback from the, I mean, both the groups and make them confounders, like it has adverse effect on such and such people, type of people.
It has adverse effects on.
On such
So
and such type of
you're
people,
asking
like,
about how to find delta, is it?
yeah.
Yeah. So under RCT, delta is precisely this. For example, let's say these estimates we obtained from an observational data set where treatment assignment happened following a randomized control trial. Then the delta between treatment B and A is just 5%, 83 minus 78. And the delta will be correct.
I see. But what if we find the confounders from by getting feedback from the patients? That is what I'm trying to say. Like,
No,
say
actually,
it
I'm
is
not able to
having adverse
understand the
effect.
question because with the RCT there are no confounders.
Okay. I see.
Yeah, with an RCT, the causal graph that we saw here, right? This X will go away. The only arrow you will have is from T to Y.
Okay.
Yeah.
Okay. Yeah. Probably I have understood it a bit wrong.
Yes.
Okay. Yeah.
Yeah.
Thanks.
Yeah. Any other question? Okay. I'll go ahead. Yeah. So as I told, we saw the recipe to treatment effect estimation, right? The first step is to fit the model F on the observations that you have. Then you will estimate effect during the inference stage as difference of outcomes under two treatments T prime and T, right? And the architecture that we follow to learn the function F is VCNet, and VCNet is a model that is already proposed in the literature. And the model, as I told, is a composition of two functions, eta and phi. Phi is the representation network. Eta is the outcome prediction network under a specific treatment T. So before going into the solution approach, we make one additional assumption to estimate continuous treatment effects. We assume that the response Y is differentiable with respect to the dosage of the treatment T, right? So we need this differentiability assumption to make sure that small change in the dosage results in small change in the outcome. This assumption may seem technical, but it is it often holds in practice, right? So to illustrate this assumption, I have included those response curves for from Google Images. These are just obtained from Google search. I do not know the specifics of this experiments, but at least these images should convince you that the response curve in real life are mostly smooth, and if they are smooth, they are differentiable, right? So with this assumption, let's get into our solution. So I need the overlap and the conditional ignorability that we saw earlier. And one additional assumption that we make apart from what is made in the literature is this differentiability assumption. So our approach is called as GIKS. It is short for gradient interpolation and kernel smoothing. The main idea behind our approach is data augmentation. So we saw on the previous slide, for every X, you have observation under one of the two treatments, right? So here, what we do is for every observed sample, we sample many new treatments and augment it with hallucinated pseudo outcomes. Indeed, you might have guessed it right, that we have two terms in the title, that is gradient interpolation and kernel smoothing. These two terms denote the two methods of how we obtain the hallucinated outcomes, right? So for every x comma t, we sample a new t prime. We estimate the hallucinated outcome y hat of x comma t prime. Once we do this estimation, we add the sample x t prime with the pseudo outcome y hat back to the observational data, and we will use this new sample to fit f theta. So I told there are we use two strategies to hallucinate outcomes. Now, which of these two strategies to use depends on the distance between the observed treatment t and the new treatment t prime for which you want to obtain y hat. Particularly, if t prime is near t, we use gradient interpolation strategy. If it is far away, we obtain the pseudo outcome using kernel smoothing or a Gaussian kernel smoothing, and this kernel smoothing involves Gaussian processes, right? Now we delve into why we need two strategies, and also we'll look upon the details of these two strategies. First, let's discuss about gradient interpolation. Because we assumed that the response curve is differentiable, we are allowed to use Taylor's expansion, right? So in particular, for treatments that are close enough, we can approximate the pseudo outcome using a first order Taylor's expansion. With the samples that are augmented using this manner, we apply conventional losses to learn the function f theta, right? So now we may argue what difference does it make, right? So you are augmenting the data set with pseudo outcomes for t prime that are very near t. Does it impact the response curve that you have learned at all, right? Now let us look at the result. Here I'm showing the response, the ground truth response curve and the fitted response curve for one data set that we considered in our paper. I think this is IHTP data set, right? So here the green curve shows the ground truth dosage response curve. The blue curve here represents a factual model that is trained just using the samples from the observational data set without following any kind of augmentation. The red curve, on the other hand, shows the response curve obtained by a model fit using the observational data set plus the augmentation that is obtained using the gradient interpolation strategy, right? And we already see that the red curve is superior to the blue curve. In particular, I would like to draw your attention to the lower dosage regime, right? Here we clearly observe the merits of the GI loss. It so happened in this data set that lower dosages receive lesser support, and thus we see that data augmentation helps in these regions, right? Moreover, we in experiments and in theory also we observed that the gradient interpolation loss exhibits a very strong smoothness inductive bias on the response curve that is learned by the model f theta. right? I think so. With this, you must be convinced that hallucinating outcomes for near treatments and then learning F on them is a reasonably good strategy, right? Now we will draw our attention to how to hallucinate outcomes when T prime is significantly distant from T, right? If T prime is far from T, we observe immediately that the first order Taylor's expansion will break down because Taylor's expansion holds only for near treatments, right? So we cannot use GI to hallucinate outcomes. And in particular, we should be bothered about one other problem. When T prime is far from T, the outcomes that you augment may be wrong, right? And therefore, it becomes imperative to augment uncertainty-aware pseudo outcomes, right? When you estimate y hat, you also need to present the uncertainty with which y hat may be wrong, right? Once we obtain the uncertainty estimates, we should come up with some novel methods to tone down the impact of pseudo outcomes that are possibly wrong. And to do that, we use Gaussian processes, right? A Gaussian process by default will give us the variance estimates, and this variance indicate the uncertainty of the estimated pseudo outcomes. So let us kind of understand this kernel smoothing strategy with an example. Now assume that we have one sample in the observational dataset where we have a patient X for which we have the label Y available under a Brown treatment T. Now our goal is to hallucinate the outcome Y hat of X at the treatment T prime. That's for the blue treatment T prime that I show here. As you can see, T prime is far from T, and we need to capture the variance associated with the outcome Y hat that you're going to estimate. And we will estimate the variance using Gaussian process that I told in the previous slide, right? So this is the only involved slide in my entire talk. It requires some familiarity with Gaussian processes, but if you, if you're not familiar, I just want you to take away one point from this slide that when the T prime is far from T, the uncertainty, that is the variance sigma square, is very essential to kind of impress upon F that this is a unreliable outcome, so don't fit it exactly. It's okay if you make an incur a loss on. Very essential to kind of impress upon F that this is a unreliable outcome, so don't fit it exactly. It's okay if you make an incur a loss on such possibly wrong pseudo outcomes. Yeah. So we apply kernel smoothing in two steps. The first step is to collect a subset of the observational data set that is denoted by DNN here, right? So DNN comprises samples whose observed treatments Ti happen to be close to T prime, right? So in essence, you check for other X, T, Y pairs, Y tuples in the observational data whose observed treatment falls within the vicinity of the treatment T prime for which you want to estimate the pseudo outcome corresponding to X, right? Once you collect this nearest neighbor dataset DNN, we obtain the mean and variance estimate using a Gaussian process that is fit on DNN. Right. So obtaining y hat and sigma square is not that interesting. The interesting part is what do you do with sigma square, right? So here I show the loss function that we use to impose loss on far away pseudo outcomes. I would like to draw your attention to just this highlighted portion in this equation here. As I told, sigma square denotes the variance of the Gaussian process prediction. And we know that if variance is large, uncertainty is more, and thus y hat may be unreliable. So what we do is we apply a softmax over the negative variance and then we use that softmax output to scale the losses accordingly, right? Essentially, this softmax term helps us to downplay the contribution of losses corresponding to pseudo outcomes that are unreliable. And in experiments also, we observed that this toning down of losses is indeed important to achieve, better results. So with this, I kind of, conclude the method. So our algorithm is to kind of, estimate the pseudo outcomes y hat for different t's, and then use them to learn the function f theta using these losses. And we saw two strategies, right? So here I present the results. So we experimented with 5 data sets, and we compared with almost all the SOTA baselines in the continuous treatment for SOTA baselines for continuous treatment effect estimation. We consistently observed that our method GAKS beats other baselines. The close competitor to GAKS was VCNet with HSIC regularizer. HSIC is Hilbert-Schmidt independence criterion. It is a kernel-based independence assessment test. It is worth noting that HSIC is specifically designed for state estimation problem, whereas most of the other baselines use what are called as targeted regularizers. And this targeted regularizer is better suited for estimating average treatment effect, that is average across the entire population. So you may wonder what happens with augmentations, right? So here I'm showing the treatment distribution after augmenting the GIKS hallucinations. We see that GIKS reduces the skew in treatment distribution, and this leads to better performance. Now we try to address theoretically why should GIKS help. We considered a simplistic setting with yeah.
Hello. Just
Yes.
Can you go just 2 slides back on the
Yes.
table where you compare? So what is the number here? Like 0.152.
0 point. Oh, this is the counterfactual error.
Sorry, this is the
Counterfactual error in estimating counterfactual outcomes.
and how do we measure that?
Simply, it is square root over the mean squared error.
So when we are estimating the okay.
Okay, I think yeah. So all of these data sets are synthetic in nature. That is why we have ground truth available for both treatments.
Okay. Got it.
So with real life data sets, it is very difficult to assess counterfactual error.
Right.
Yeah, sorry, I missed that point. Yeah.
Okay.
Yeah. So all of these data sets have synthetic Y function. But the problem setting remains the same. In the observational data, you have Y available for just one treatment, and that treatment is selected in a biased manner.
Right.
Simply during inference, we obtain Y using the synthetic functions, and then we estimate the error.
Oh.
Yeah. Yeah. So here we were kind of addressing theoretically when should GAKS help. And it is a very toyish setting in the sense we have one Gaussian covariates that are one-dimensional, and our output Y also follows Gaussian distribution. And in this simplistic setting, we are able to come up with two criterion under which GIKS achieves success when compared to a factual model that is only fit on the observational dataset without any augmentation. Right. The first condition is that the nearest neighbor dataset that you collect on which you fit this GP, right, that should be not empty. The second criterion is that among the samples that are present in DNN, we need instances that are similar to X for which you are hallucinating the pseudo outcome. I mean, these two are kind of very intuitive conditions, and that are necessary to kind of make GIKS achieve success. So we conducted several other ablation studies and sensitivity analysis to motivate why motivate the robustness of JK's approach, and I defer those details to in the paper. Please refer to our paper for more details. So in conclusion, we addressed, individualized treatment effect estimation, particularly when treatments take continuous values. Our main strategy was to augment observational datasets with new treatments and hallucinate outcomes for them. We devised two strategies. One is called gradient interpolation, other is called kernel smoothing. Because the response curve in real life is also going to be smooth. For gradient interpolation, we need not worry about uncertainty. Whereas for kernel smoothing, because it estimates outcomes for faraway treatments, we need to have reliability estimates so that you can tone down the contribution of losses corresponding to unreliable hallucinations. So we devised two strategies for estimating hallucinated outcomes. So we conduct experiments on benchmark ICTE datasets, and we are able to show statistically significant gains over other SOTA approaches. In future, we would like to precisely characterize the characteristics that the observational dataset should satisfy for JKs to be successful. Like we saw, two properties that the observational dataset needs to meet in a storage setting. Now, if we were to do a similar kind of theoretical analysis for a much general dataset, what will the criteria turn out to be? That's an interesting question that we would like to address in future. Thank you so much for listening to me. I think we have 10 minutes.
Okay. Yeah, first of all, thank you, Lokesh, for the wonderful talk. So if anyone have any questions, you can ask.
I have a doubt.
Yeah, go ahead.
Yeah, sure. So when you're going for this continuous treatment assignment, let's say I'm giving a drug X, a drug amount T, and then I go T plus some delta, and then I go from T to T plus some delta 2. So I'm observing the Kate effect in each of these cases. Okay, is this additive in nature? Like if I directly jump from T to delta 2 instead of going in 2 steps, so are these additive? These treatment effects?
Yeah, they're not additive, right? So this is one ground truth response curve in IHTP dataset.
Mm-hmm.
So we see that the curve is not even unimodal. So
okay,
yeah, they're not additive in general.
Okay, so okay, so this will depend on the sensitivity of the treatment on the outcome, right?
Yes, that's right. Yes.
Hello.
Yeah.
Lokesh, you can hear me?
Yes, I can hear you. Yes.
Yeah. So, I mean, my essential understanding of the problem and what you're doing, right, is that essentially you have, in your observational data, some discrete set of points which are available. X and T, with X being an unknown confounding variable. And what you are trying to do is, using kernel smoothing, you're sort of estimating a distribution around, in that space.
Right.
With, for example, if I keep X fixed and I move T from T to T dash, what is the distribution, and you essentially convert the distribution into a number outside. So have you considered also looking at other ways of estimating this distribution beyond just Gaussian? Because nowadays, obviously, there are a lot of very fancy estimators. You have a lot of generative techniques which also estimate distributions within them. So Gaussian is obviously very nice to have and does a good job. So would you think that other estimators would help? Maybe another neural network which also estimates distribution close to in that space based on the data? Or does the question make sense?
Yeah. So question, definitely, it's a great question. So when we do Gaussian process, right? So we assume that the y hat follows a Gaussian distribution. Right. When you're fitting this model, you're kind of assuming Gaussian likelihood. when things are Gaussian,
Yes.
things are very tractable. If you move out of Gaussian assumption, then you have to resort to techniques like Monte Carlo sampling, etc.
Right.
That
Yes.
training that systems will become really difficult.
Yeah, so the reason I ask is because a lot of at least in what I have seen, I mean, probably not in the domain that your problem lies in. A lot of these systems, although they require a lot of observational data, that is true. They are now capable of estimating arbitrary distributions. Okay, whereas Gaussian has its limitations. I mean, you can move to a mixture model, which is very difficult to estimate because of untractability, like you said.
Yes.
So, I mean, I understand. I mean, that may not be something that is useful to you right now. So, or it may not give you what you want.
Particularly relevant for, I think, real world benchmarks. But at least the data sets as a field stands today, right? We are restricted to synthetic data sets because you don't have Y under, you don't have counterfactual Ys, right? So at least for these data sets, GPs were adequate.
I see. Okay.
But in general, if you want multimodal distribution around Y hat, then I think we have to go for much more sophisticated techniques.
Yeah, I see.
Yeah.
And one more question regarding, in one equation in your paper, there was a K, which was basically the posterior of the Gaussian, the mean of the posterior that you compute, right? So there was one K which uses phi of X and phi of capital X. I'm not sure if you remember. Okay, so you don't have the Gaussian. So my confusion was that that K is essentially just the covariance of the nearest neighbors that you have taken, right?
Okay, you're talking about the GP equation.
The GP equation, because it had a small x as well as a capital X. That's why I'm asking.
Yes.
Capital X was a set or a matrix.
GP needs two things, right? X and Y. So the capital X denotes the covariates that you collect in this DNN dataset.
Yes.
So
yes,
DNN is a
and eventually
right?
it is
Y.
Yes. I see. So and eventually it is just the estimates that you get after doing the posterior from the evidence. That's all.
Right.
So you get the Gaussian posterior and the mean of that. Okay.
Exactly. That's right.
Yeah, thanks.
So the capital X is nothing but stack of all the Xi's that fall within DNN.
Okay, understood. So it's a matrix and you do from there. Okay.
It's a matrix, right? So I think I'll add one more detail. So given the nature of this problem, right, the kernel K should depend on both X and T. Essentially, if you think through, intuitively a GP is nothing but a nearest neighbor classifier in some sense, right? Now, for this, for the X, because I have observed brown treatment, if you want to hallucinate outcome under blue treatment, you will latch on to another observation in the observational data set whose X happens to be similar to this X, and you have outcome available under a treatment close to T prime. Right? If you have a nearest neighbor, both in terms of X and T prime, that is the outcome you will kind of borrow. Am I making sense? Hello.
Yes.
Kishal, can you hear me?
Yeah, I can hear you.
So for this GP, right, essentially you should define a kernel. You should define a joint kernel with both X and T. Right. So we kind of get rid of this joint kernel by this intermediate step DNN, where we collect samples that are close to T prime. This lets us define a kernel only using the covariates X. Does it make sense?
Yes, but I have a question regarding that. So the set of nearest neighbors that you choose, right? Those are based on this Ti minus T dash being less than epsilon.
Yes.
But what about the x's? these x's in their embedded space may be very, very far off. So, for example, you may end up choosing
Exactly. I think
you know,
got the
nearest
point.
neighbors of the smaller stones as compared to the larger stones that you wanted to choose.
I think you got the point. So if all the x's that lie within DNN are far from the covariate for which I need to estimate y hat, that will be reflected in the variance, right? A GP variance is a function of just the x's.
I
Right?
see. Okay,
If
so
you don't
you'll scale
have-
the loss accordingly.
I will scale the loss accordingly. That is the essence of this GP phase.
Right. Okay. Mhm.
Yeah.
So any other question?
So Lokesh, one of the members of the group wanted access to the GitHub repository for your code. So can you
Yes.
share the link? Yeah.
Link, yes. The code is available.
Mhm. Actually, they tried to access it through your paper, but they said that it's not working.
No, when did they check?
Earlier today.
Oh, is it okay? I will paste it in the Teams. Where is the comment?
So the comment came in the Slack workspace. So if you could
No,
just
no,
paste it
in
here,
Teams,
I'll forward it.
How do I paste it here?
In the chat box, if you paste it, that should be fine.
I'm not able to see the chat box. I think. Maybe I will send the link to Kishale.
Sure.
Yeah. Or if you go to the archive link, right, you should be able to find that. Yeah, the link in the archive page works. So.
Okay. Great.
Okay. Okay, then if no one has any other question, let's thank Lokesh again for this nice talk. And yeah, we will see again in the next week. Okay. Thank you. Bye.
Yeah, thank you. Bye, guys.
Bye.